Okay, hello, welcome. This is the second part of the recording that we'll be providing in lieu of the recording of Wednesday's lab. In the second portion of the video, I want to go over the second algorithm, the LU decomposition solver, and the talk a little bit about the actual problem, the final project you need to submit. So let me share my screen. Okay. So the LU decomposition algorithm works on the premise that, well, if we recall, we will have some kind of matrix of coefficients A times a vector of variables X equals some vector of constants B. And the LU decomposition is starts from the principle that we can write A, the vector A, sorry, the matrix A in a matrix L times a matrix U, which is a lower triangular matrix with zeros on the rest of the matrix times an upper triangular matrix with zeros on the rest of the matrix. So we are saying A is equal to L times U. So writing down the rest of our problem, L times U times the variables X equals B. And why do we care about this? Because we can call these guys here, these guys will be a matrix U times a vector X that will be another vector. We can call these guys a vector Y, and we can write the problem above as L times Y equals B. So this is another linear problem. It has exactly the same structure as our original linear problem. And this has a particularity that the matrix of coefficients is triangular. So in this case, it's lower triangular, but we can do something very similar to what we did at the end of Gaussian elimination. At the end of Gaussian elimination, we did backward substitution because we had a lower triangular. So we had some element here times its single variable x3 or xn in. So let me write that more neatly. So at the end of Gaussian elimination, we had some matrix of coefficients with an element here, 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 in all the diagonals, and everything in between, and zeros here, times a matrix of variables x1, we'll call them x2, dot, 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 all the way to the last 10, xn, equals some b's, b1, b2, dot, 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 bn. So we had this last row that only had one coefficient that was not zero times the variables equals bn. So we basically had this guy times xn equals bn. So that makes it really simple to solve for xn. We just divide this guy over this guy, and that's it. And we will go back to the previous line where we would have two elements. So xn minus 1 times this guy plus xn times this guy equals some guy over here, but we already know xn, so we actually only have one variable, and we solve for it, and then we go to the previous line, and so on and so forth. That's backward substitution. In this case, we will have something very analogous, but we start from the top, where we have this guy times something equals the first variable. Then we have two terms, but we know the first one, and so on and so forth. So in here we would actually do forward substitution, which is really simple. It's exactly the same as backward substitution. It just goes from the top to the bottom. So it is very simple for us to solve for the y's. But the fact is that we don't really care about the y's. The solution for our linear problem is the x's. But if we know the y's, we also know, we wrote it down up here. We know that u times x equals the y's. And if we already know the y's, this is another linear problem. And we can use the fact that u is upper triangular to run a backward substitution and find the x's. So in here, this is a backward substitution. All right. So these two stages, these two algorithms are really, really simple. The difficult part is on how we actually get these two matrices, L and U. So let's look into that. So we know that A is equal to L times U. And for simplicity, so we know that L is lower triangular and U is upper triangular. So for simplicity, we will assume that L has ones in its diagonal and then some coefficients. I will work as before in an example by 3 by 3, but this is generalizable to any square matrices. So some matrix L 2 1, L 3 1, L 3 2, zeros here. And for U, this is upper triangular. Here we will not make any assumptions about the diagonal. U 1 1, U 1 2, U 1 3, 0, U 2 2, U 2 3, 0 0, U 3. Right? So this is equal to A, and A will be A11, A12, A13, A21, A22, A23, A31, A32, A33. All right. So how do we find this? As before, we will go column by column. So we will look at the first column, in this case of two matrices. So of this matrix and this matrix. So let's solve for the U first. We know that L times U will be equal to A. So we know that if we, let me change the color to green this time. We know that if we multiply the first row by the first column, we'll get the element in the first row, first column of A. So we basically know that that means that if we multiply 1, which is this guy, times U11, this guy, plus second element 0 times second element 0, plus third element 0 times third element 0, that is equal to that position, row 1, column 1 of A. So this guy, so A11. So this simply means U11 equals A11. All right, so we know this guy. And we know that, remember that we are going by columns. So we know this guy, and we know that these and these are 0 just by definition. So let's look at L1 now. In L1, we already know that this guy is 1. We chose it to be so. So let's go to this guy. About this guy, we know that if we take this row and multiply it by this column. So second row, first column, we will get second row, first column of A. So this guy. So we know that if we multiply first element, this guy, L21 times first element, U11, which we already know. We got it here. Plus second element, this guy, times second element. So say 1 times second element, 0. Plus third element, this guy, 0 times third element, this guy, 0, equals, as we said, second row, first column of A, this guy. So A21. So from this we know that L21 equals A21 over U11. All right. So again, we are still on column 1. So the only element we still don't know is this guy. Oh, excuse me about that. This guy, L31. Just as before, we know that if we multiply this row times first column, this column, we will get third row, first column of A. So this guy. So first element, this guy, L31 times first element, U11, plus second guy, L32 times second guy, 0, plus third guy, 1 times third guy, 0. So here we're leveraging that these zeros get rid of this guy, which we don't know. And if there were more, if L was bigger, it was not a 3 by 3, then those would also disappear. So all these guys equal again to this guy, A31. So we have that L31 equals A31 over U11. All right. So let's go over an example. I want to go through the same example that we have in the presentation just to show this quickly. I'll do this here. So the set of equations we want to solve are 3x plus 7y plus z equals 5, negative 2y. This should be a plus. Oh, excuse me, my pen is behaving oddly. Negative 2y plus 4z equals 15. 3x minus 2y minus z equals 0. So we want to go over these set of equations. So, and we want to decompose the matrix of coefficients 3, 7, 1, 0, minus 2, 4, 3, minus 2, minus 1. We want to decompose these into L and U. So let's look at we just did here. So we got U11 equals A11. So U11 equals this guy, 3. L21 equals A21 over U11, which is this guy, 0 over this guy, 3. So 0. L31 equals A31 over U11. So this is this guy, A31, 3 over, sorry about that, over U11, again this guy, so 3. So that's 1. And we now have our first column for both L and U. So for L, we will have 1. So by definition, 1's in the diagonals, and 0's on top, 0, 1, and some coefficient that we still don't know, 3, 2, times u, which will be u11, we just got it, it is 3. Zeros down here, we still don't know these guys or these guys. Okay, so we are done with the first column of both of them. Now, a very important issue here. What happens if you're gonna be doing this? What happens if this guy, so basically U1, and U1 means A11, so this guy, what happens if that guy is 0? If that guy is 0, then our all algorithm will blow up and it will give us an error. So what do we do in this case? Before starting to work with the column, we would pivot, just as in Gaussian elimination. We will look at the column and look at which is the biggest absolute value in that column. And we will swap those two rows, and then we will go on to do the LU decomposition, right? Now, this is the general idea of how you would solve all of the coefficients. You can carry out the matrix multiplication and figure out which coefficient is which, but that is very tedious to do, and it is a little bit hard to generalize. So in the presentation, we gave you the general formulas to do on this. So basically what we want you to do is to go for some counter j. So this will count the columns. For some counter j that goes from 1 till the end. So so we will be cycling through the columns. In the middle, we will be, so first of all, we will do some pivot for that column. We don't want to run into issues of dividing by 0. And then we would start a second loop. We would start a second loop from within the column loop, and we will go through the rows to solve for both L and U. Okay, sorry about that. I'm just looking through my notes. So we will start our second loop for I, which will be counting the rows, equals 1 through j, 1 through the actual column till until which we are currently in. So why is that? Here we'll be solving for u. So u equals an expression that we have in our presentation. So, but I want to emphasize on the rows that we'll be working on. We will only be working down to the diagonal. So if we are on the second, we're on the second row, so j equals, sorry, second column, j equals 2. So we are here, down here, we'll be working for I equals 1, I equals 2, and then we stop because everything below the diagonal will be 0. So we will just want to get to I equals j. So we will have that, or u ij, so the row and the column, current row and current column, equals, and this is there in the presentation, a indices I j minus the summation of k equals 1 through the last row of L I k, oh, sorry, I comma k times u k comma j. So these are the current row, current column, and that'll be the expression for u. And all these elements should be known by this point. And this summation You could make an inner loop over k if that's the way you want to do it. You can also express it as a summation with the function sum. So that's up to you. That this is your code, but that is the general expression for you. Then we end the loop for you, and then we do another loop for I equals j, I think this is j plus 1 actually, through n. Li comma j will be equal to 1 over u j comma j, so current column, times ai comma j minus the summation of k equals 1 through j minus 1 of li, excuse me about that, li comma k times u k comma j. So again, these are the current row, current column, and you can choose to do a loop over k if that's what you like, or do a summation. It's up to you. But this is the general expression. We end that loop. Excuse me here. I wanna correct this j plus 1. Why j plus 1? Again, we are trying to solve the elements of L. And for any given column, if we look at how L should look like, L for any given column, L will have 1 on the diagonal and elements below. For the second, it will have a 1 on the diagonal and elements below. We don't want anything. We already know what is there on the diagonal. It's a 1, so we don't need the j comma j element, and we don't need any row before j. We don't need any row above this because we know that all of those elements are 0. All right, so we start counting from j plus 1 all the way to the end. So in the first column, we would start here all the way down. In the second column, we would do this. And in the third column, we already know the third column. All right. So this is more or less what we want you to do. We will cycle over all the columns, and inside the columns, you will be cycling through the elements, and you will be using this and this expression for L and U. Once you have L and U, it is really simple. You will write the set of temporary variables Y from forward. You will find those from a forward substitution of the expression L times Y equals B. And Y is a temporary set of variables. We don't really care about them. So this is a vector, this is a vector. We care about X, which we will find via backwards substitution of the expression Ux equals Y. All right. So that is basically all you need to do for this solver, for the LU solver. Again, I have updated the PDF to show, to clarify the fact that both functions will have, they will be solving an expression AX equals B. So you will have as inputs A and B to your solver, and it will output the solution X. So input, output. So that's for both solvers. Both will have this structure down here. Now for your actual project is a pretty interesting one. So you will have a set of given points, given locations for a planet. It's actually a set of locations for Mars, measure for with some instrument, and you know that those locations should be describing an ellipse because that's how planetary orbits work. So you should have some. You should have the star, the sun, in the orbit, and the planet Mars, I'll draw it in red, should be describing some kind of elliptical orbit around the sun, with the sun in one of its foci. So if this model was perfect and the instrument that was taking the measurements were perfect, the set of points would be here along the ellipse, perfectly along the ellipse. But the fact is that in many science and engineering applications, your instruments and your models, they are not perfect. So they are they collect noisy data. So instead of points describing a perfect ellipse like that, you will have many points closely describing an ellipse like that. So you will have a cloud of points. If you plot them, it will be evident that they don't really describe an ellipse. They are about an ellipse, but not quite. So this ellipse, so you basically want to find the ellipse that most closely matches all of these points. There is no single one ellipse that will go through all of these points, because for any ellipse, it's impossible to go, let's say, through these these 5 points, for instance. There's no ellipse that will go through these 5 points. But we can find an ellipse that will be as close as possible to all of the points that we collected. And this ellipse, this optimal ellipse, will be described for some W, for some vector W. There's an expression in your PDF that shows that generally an ellipse will be described by some W1 times x squared plus some W2 times y squared plus some W3 times x times y plus some W4 times x plus some W5 times y. This will be equal to 1. Excuse me about that. This will be all equal to 1. So your vector W is actually the vector that contains all those coefficients, W1, 2, all the way to 5. Okay, so essentially finding this W means finding the ellipse. This W describes an ellipse. And since we cannot really go through all of the points, we know that not for all the points we will be able to have an equation where the w's times the variables will actually give us 1. But we want to make this equation as close as possible, so we change our problem to something like minimizing the w times, actually the other way around. We want to be minimizing the phi. These are the polynomial fixtures. So phi will be this x squared, y squared, xy, x, and y. So we'll be minimizing phi times w minus the vector of ones. So this is a vector. So this is just a vector that has ones all over it. We want to minimize the norm of this. All right. So this essentially means that we want all of our equations. So our equations will be phi times w. We want all of them to be as close to 1 as possible. So as close to describing this ellipse as possible. So in your PDFs, you will find an expression of the type. Let me check my notes because I don't want to give you false information. So the solution of this problem is a W optimal equals V transpose times V, all this inverse times V transpose times the vector of ones. But we want to write this in a way that where we can actually use our solvers and look at our solvers. Also, our solvers solve a problem of the type A times X equals B. And this is not exactly what we have. Here we have some this expression, which is called the pseudo inverse of the matrix. And that is not quite what our solver does, but we can rewrite this as V transpose times V times W equals V transpose times 1. All right, I'm just doing some linear algebra in here. And this guy will be our matrix A. If I recall correctly, it's 1600 by 1600, but I would have to double check that, times or vector W. Actually, I'm wrong. So this guy is 1600 by 5. This is the transpose, so it's 5 by 1600. So this will be a matrix A, that's 5 by 5, times our W, that is 5 by 1, equals, this is again a 5 by 1600, and this is a vector of 1s, that is 1600 by 1. So this multiplication to the right, this guy over here, this gives us some vector. I will call it, I don't know, V for vector, that is 5 by 1. All right, so you will have this expression. You have your A and you have your coefficients and you have your constants. So you can plug this into your Gauss solver and into your LU solver to get a W from Gauss. So W Gauss and a W from the LU decomposition. And that's it. This will be your ellipse for Gauss. And this will be your ellipse for LU decomposition. So we want you to plot the scatter data as we show above, and we want you to plot these two ellipses on top of it. And for that matter, plotting these, even when you already know the W, it is not a trivial task. So we are providing you a code in the PDF to plot these, and you only need to change this W, because the plot so the plotting code has some generic variable called W in there. So replace this W by your W Gauss and your WU LU, and that will give you your two ellipses. You just modify that code. You should be able to modify that code without too much trouble. Okay. So that is basically all we want you to do for this project. We want you to time these two solvers just to let us know how do they compare. Is one a lot faster than the other? Are they about the same speed? And yeah, we want you to show us these graphs in your presentation, these plots. And that's it. That's the end of this video. I wish you all luck during this project. Dennis and I will both be holding optional office hours next week on usual lab time. So if you have any questions, please do attend. This project is meant to be challenging, but it's not meant to be impossible. So if you have any problems, if you're stuck, please do attend and we'll try to figure it out. Okay, I'm gonna stop the recording.